So today we're talking about finding the area between a curve and the x-axis. And so I know we've already talked about, what's an integral, right? An integral is the area underneath the curve, right? Generally, when we talk about that, we talk about, some function that's above the x-axis for its entire domain. But now we're going to start dealing with some where they might cross through the x-axis, and where we have to worry about that. So when we talk about finding the area, specifically the area, any section of the curve that's above the x-axis, the area is always positive. So the integral always comes out to be positive. So from a to b, the integral would come out to be a value that's greater than 0 because we are above the x-axis. But if we were to integrate from b to c, the value of the integral here would be less than 0 because our function is below the x-axis, right? And so that's very important because when we talk about the area between a curve and the x-axis, we want to take into account both the stuff that's above and the stuff that's below, but we want the stuff that's below to be indicated as a positive unit of measure because we can't have negative area. Right, so if we were to find the area between the x-axis and this curve from A to C, we would have to split it at B and integrate from A to B, and then integrate from B to C, and the part from B to C we'd have to take the opposite of. We can't just integrate from A to C because then you'll get some positive and some negative and it'll cancel out and you'll get some very small value for your area. Does that make sense to everyone?
Yeah.
Cool. So that's the basic idea of what we're going to do today. So sort of the steps we're going to take when you're asked to specifically find area is graph your function and see if there's any discontinuities. So like if you have a hole in it somewhere, you want to break up your interval at that hole. That's not going to happen very often. But what will happen often is you will have a place where your function crosses through the x-axis. And so like I said, we'll integrate each section separately, take the opposites of the pieces that are below to make them positive, and then add all of our areas together to find the actual area between the curve and the x-axis from, in this case, A to C. Good? Hopefully. Let's do one. So and this one should be really easy. We're looking for the area of the region bounded by the x-axis and two different lines and a curve. So the lines are x equals 2 and x equals 5. And then we have the curve f of x equals x squared plus 1. So we're just going to quickly sketch that. Okay, here is x squared plus 1. There's my parabola. It looks okay. And I guess I didn't do a great job there. It should probably be a little more symmetric, but that's fine. Here's x equals 2. And here is x equals 5. And so if we look at the region between the curve, x squared plus 1, the line x equals 2, the line x equals 5, and the x-axis, we are talking about a region that is only above the x-axis. Would you all agree with that?
Yeah.
Okay, so this one's easy. In order to find that area, all we have to do is integrate from the left to the right, 2 to 5, that function. We don't have to worry about splitting it up. There's no discontinuities. There's no sections below. This is just a regular old integral. Should be very easy. X cubed over 3 plus x. And we need to evaluate it from 2 to 5. So we'll plug those in, giving us what, 125 thirds plus 5 minus 8 thirds plus 2. And what does that end up giving us? 125 thirds minus 8 thirds should be what, 117 thirds? And then plus 5 minus 2 would be plus 3. So that'd be 126 thirds or 42. And when we talk about area, even if there's no units given, we're going to indicate it with units squared. Good or no? Everyone okay with that?
Yep.
All right, that should be easy, no different than what we've been doing in the past. Now what's going to make it a little bit more difficult is if we get a more difficult function that crosses through the x-axis. So we've now got the area of the regions between this function and the x-axis from -2 to 3. So how do I graph this function?
You find the x-intercepts.
Okay, x-intercepts. So we'll do that by factoring it, right? And setting it equal to 0. X minus 3x plus 1 equals 0. Told us we have x-intercepts at x equals 3 and -1. And then a y-intercept of -3. And we know it's a parabola. It's going to go through those 3 points, and we know that it opens up. So it's going to look something like that. Everybody agree with that? Hopefully that's good. So we want, though, the regions between -2 and 3. So if I'm going from -2 to 3, there is a portion of that that is above the x-axis, and there's a portion of it that is below the x-axis. So we've got to split it up into 2 different integrals. The first one from -2 to -1. And that's of x squared minus 2x minus 3 dx. And then the second one, which is from -1 to 3 of the same function. But what do we know about that one? This one comes out to be negative. And we need to take the opposite of it, right? So instead of adding these together, I need to take the first one and subtract the second one. Because that'll effectively turn this into a positive value that I can then combine with the positive value from the -2 to -1 integral. Good or no?
Good.
All right. So we got x cubed over 3 minus x squared minus 3x from -2 to -1 minus same integral, right? X cubed over 3 minus x squared minus 3x from -1 to 3. And now we just evaluate. And it gets a little messy because of all the arithmetic and the minus with the more minuses and all that, but that's the way it goes. -1/3 minus 1 plus 3 minus -8/3 minus 4 plus 6 minus, and then all of this is going to be subtracted here. I guess I can just do it with the bracket. 27/3, which is 9, minus 3 squared, which is 9, minus 3 times 3, which is 9. And then that's a -1 there. So -1/3 minus 1 plus 3. Everybody agree with all that?
Yep.
Cool. And then now it's just some arithmetic to finish solving, which is a little bit of a pain, but that's okay. -1/3 minus 1 plus 3, that's -1 plus 2, which should be 5/3. Then we're going to have minus, we got -8/3 plus 2, which should be -2/3. So we're subtracting -2/3, that would be a plus 2/3. Then we got minus all of this, 9 minus 9 minus 9 is -9. And then minus, we got -1/3 plus 2, right? Which is, like we said before, 5/3. We got -9 minus 5/3, giving us 7/3. And then -9, that's -27/3, right? Minus the 5 is -32/3. We got minus a -32/3. Giving us 39/3 or 13 units squared. Good or no? Any questions on that?
Nope.
All right, let's do one more, and then that will be good for the day before we come back and start talking about finding the area between curves tomorrow. So we want the area of the regions between sine x, cosine x, from x equals 0 to x equals pi. Now, we might not know exactly what that graph looks like. Do you agree? You probably, in fact, don't know exactly what that graph looks like. If you do, then good, but if you don't, that's okay. What we need to concern ourselves, though, with is when it crosses through the x-axis on the interval between 0 and pi. So how do we determine when that crosses through the x-axis? Well, we have to set it equal to what do we set it equal to see when it crosses through the x-axis?
0.
Set it equal to 0. And since this is a multiplication of two things, the zero product property says if one of them is 0, the whole thing is 0. So set them both equal to 0 separately. This one gives you 0 and pi on the interval from 0 to pi. And this one gives you pi over 2. Everyone agree with that?
Yep.
All right, so we know that this function has x-intercept at 0, pi over 2, and at pi. And we'll probably need to figure out when it's above the x-axis and when it's below the x-axis. So if we were to evaluate just on like a sign chart here, here's 0, here's pi over 2, and here's pi. If I plug in something between 0 and pi over 2, like pi over 4, what do we get? We get a positive times a positive. F is greater than 0, right? And if I plug in something between pi over 2 and pi, like, a second quadrant angle, sine is positive, but cosine is negative. So we know that from 0 to pi over 2, the function is positive, and from pi over 2 to pi, the function is negative. So we need to do this integral from 0 to pi over 2 as a positive one, and then we need to subtract this one because it comes out to be negative. Does that make sense to everyone?
Yes, it does.
Oh, good. And we will subtract pi over 2 to pi. And how do we integrate sine x, cosine x?
U substitution.
U substitution, exactly. So what's u going to be? U is going to equal sine x. And du will be cosine x dx. And when x equals 0, what is u going to equal? Yeah, 0. And when x equals pi over 2, what's u going to equal?
1.
And when x equals pi, what's u going to equal?
0.
0. So we got a little interesting thing happening here. We end up with an integral from 0 to 1, right? Minus, sorry, I should probably write the function there, u, right? Of u du, minus the integral from 1 to 0 of u du. And what can I do with something where I have a lower limit is larger than the upper limit? I could flip those and change the sign. Or effectively just, if I have this integral and this integral, that'd be 2 of that integral, wouldn't it? Which would give us 2 times u squared over 2, evaluated from 0 to 1. And what does that give us? That just gives us, 2's cancel, right? It just gives us 1 minus 0, or 1 square unit. Good or no? Any questions on that process there? No, no questions. Everyone's good. All right.
Could we also do it by like like putting the subbing sine x back in and just evaluating like that. I guess this is easier though.
Yeah, I mean, if you want to put sine back in and change everything back to zeros and pi over twos and pies and evaluate it, you can. But I feel like you already turned it into these. Why turn it back and then have to reevaluate them again to put it back into these? You're really just doing like 3 times as much work if you do that. So your choice, though. You'll get the same answer.